Today's topic is tracing of curves. So there are 7 characteristics, namely asymptotes, intersection with the axis, symmetry and double points, tangents, and concavity and convexity. These are the characteristics with the help of which we may trace any curve. But considering all these characteristics is very time consuming, and as we know, in examination we have limited time to solve multiple questions, so it is not advisable to consider each and every characteristic to trace a curve. So in this video I am going to tell you 4 essential minimum number of the characteristics of a curve with the help of which we may trace any kind of curve. So if you like this video, please share it in your circles and subscribe my channel. The most important characteristics of a curve plotted on paper are: number 1, intersection with axis. Number 2, symmetry. Number 3, asymptotes. Number 4, double points. So we will discuss each and every of these 4 topics in details one by one. So number 1, intersection with the axis. Intersection with the axis means at what points the curve intersects x-axis and y-axis. So intersection of the curve with x-axis, we substitute y is equal to 0 and then find the possible values of x. And putting x is equal to 0, find the possible values of y, which tells us at what points the curve intersects y-axis. Second most important characteristic is symmetry. So for that purpose, there are different cases which we have to remember. Case first, if replacing x by minus x, the equation of the curve doesn't change, the curve must be symmetrical about y-axis. Case second, if replacing y by minus y, the equation remains the same. The curve must be symmetrical about x-axis. Case third, if replacing x and y both by minus x and minus y, the equation of the curve remains the same. The curve is symmetrical about the origin. Now case fourth, if interchanging x and y in an equation, the equation of the curve remains the same. The curve is symmetrical about the line y is equal to x. These are the 4 points of symmetry which we must keep in mind while plotting a curve. Now we are going to discuss the third important characteristic of a curve, that is asymptotes. What is asymptote? As you might have learnt it, the asymptote is a tangent to a curve at infinity. It looks like So if this is the curve, this is an asymptote. So there are two kinds of asymptotes: parallel asymptotes, that is parallel asymptotes to x-axis and y-axis, and oblique asymptotes, that's to a curve which is neither parallel to x-axis nor to y-axis. So how to find asymptote parallel to x-axis? The process is very easy. We need to observe an equation the coefficient of the highest degree term of x is variable or constant. If the coefficient of highest degree terms in x in an equation is variable, there must be asymptote parallel to x-axis, and to find, we need to equate that variable coefficient of the highest degree terms in x to 0. For example, if the highest degree term of x in an equation is y minus 3x cube. X cube is the highest degree term in an equation and its coefficient is y minus 3, which is a variable coefficient. So if we equate y minus 3 to 0, it gives us an asymptote parallel to x-axis. Similarly, to find asymptote parallel to y-axis, we need to equate the variable of the highest degree terms in y to 0. For example, x minus 2 y raised to the power 4 is the highest degree term in y, and its coefficient is obviously variable coefficient because it has x. So there must exist an asymptote parallel to y-axis, and that is obtained by equating the variable coefficient to 0. So we need to equate x minus 2 0. So x is equal to 2 is an asymptote parallel to y-axis. So this is the simple way to find asymptote parallel to x-axis or parallel to y-axis. Now we will discuss how to find oblique asymptotes. Now, how to find oblique asymptotes? In order to find oblique asymptotes, first we need to observe the highest degree terms in the equation of the curve to be plotted. So in the highest degree terms, we need to substitute x is equal to 1 and y is equal to m, and whatever expression we get by substituting x is equal to 1 and y is equal to m in the highest degree terms, we name it as phi m n, where n is the highest degree. So whatever expression we have, that is phi m n. If suppose the highest degree term is 3 degree term, so that will be phi m3. If the highest degree term are of second degree term, so that will be phi m2. And if the degree of the highest degree terms is 4, then that is called phi m4, and so on. So we find phi mn. So after that we have to equate it to 0. We need to equate phi mn to 0 and solve it for m. Now for example, there are 3 values of m and all the 3 values are distinct, that is m1, m2, m3. These are the slopes of the asymptotes to the curve. In step 2, now we need to find out the y-intercepts made by those asymptotes, and for that purpose we use the formula C is equal to minus phi m n minus 1 upon phi dash m n, where phi m n minus 1 is the expression obtained by substituting x is equal to 1 and y is equal to m in the second highest degree terms. So suppose this is 3, So third degree terms are the highest degree terms, so phi mn minus 1 must be second degree terms. So after that we have to substitute x equal to 1 and y is equal to m in the second degree terms to find phi mn minus 1, and we need to differentiate phi mn with respect to m, that is phi dash mn. So we have to substitute the values phi mn minus 1 and phi dash mn. Then we have to find the value of c with the help of this expression by substituting these distinct values of m, that is m1, m2, m3. So we need to find out when m is equal to m1, c is equal to c1, which is obtained by substituting this value of m in this expression. Similarly, we find for m is equal to m2, c is equal to c2, and for m is equal to m3, c is equal to c3. After obtaining these three values of c, corresponding values of c for these different values of m, in step 3 we substitute these pairs of the values of m and c in y is equal to mx plus c 1 by 1. So we get three asymptotes, that is y is equal to m1x plus c1, y is equal to m2x plus c2, and y is equal to m3x plus c3. But for repeated values of m, that is if m is equal to m1 m1, we use the equation c square upon factorial 2 phi double dash m n plus c phi dash m n minus 1 plus phi m n minus 2 is equal to 0 if there are only two repeated roots, and if there are three repeated roots, so we need to use c cube upon factorial 3 phi triple dash m n plus c square upon factorial 2 phi double dash m n minus 1 plus c phi dash m n minus 2 plus phi m n minus 3 is equal to 0, and so on. Now the fourth characteristic which we need to discuss for tracing a curve is a double point. So double point is a point where a curve intersects itself. The point at which a curve intersects itself, that point is said to be a double point, and there are two kinds of double points. One is called a node and the other is called a cusp. At a double point, if two tangents can be drawn, that double point is said to be a node, and it looks like this. So as you see, these two tangents can be drawn at this double point. So this is called node. And the double point at which only one tangent can be drawn at the point of intersection, that is called cusp. So this is like so here only one tangent can be drawn at the point of double point, which is this. So this is a cusp. So simply a double point at which two tangents can be drawn is called a node, and the double point at which only one tangent can be drawn, that is called cusp. Now how to find a double point? Suppose fxy is equal to 0 is the curve to be plotted. First we need to find out first order derivative, partial derivatives of f with respect to x and y. That is, we need to find out del f over del x and del f over del y, and equating them to 0, both of them to 0, we find the possible values of x and y, which gives us the possible double points of the curve. After that, to determine whether the double point is a node or a cusp, we need to find the second order derivative, that is the second order partial derivative. First, we need to find out del 2f over del x square by differentiating del f over del x with respect to x again partially, and then del 2f over del x del y, that is differentiating partial derivative with respect to y again with respect to x, and del 2f over del y square, that is the second order partial derivative of del f over del y with respect to y again. So del 2f over del x square, del 2f over del x del y, and del 2f over del y square. Then we find the values of these expressions, these second order derivatives, at those points which are obtained by equating del f over del x and del f over del y to 0. That means the possible double points. We find del 2f over del x and del y whole square minus del 2f over del x square del 2f over del y square. If the value of this expression is found to be greater than 0, that is positive, then the double point is a node. Double point is a node. And if the value of the same expression at a double point is equal to 0, it must be a cusp. Now let us take an example. Suppose we have to trace the curve x square plus y square into x minus a, x square minus y square. So first characteristic we need to discuss is intersection with the axis. To check intersection with the axis, as we have discussed, first we have to substitute y is equal to 0 to check the intersection with the x-axis. So if we substitute y is equal to 0 in the equation, obviously we have x square plus 0 into x, that is x cube, and minus a, and here x square minus 0, that is x square 0. Now taking x square common out of it, we get x minus a is equal to 0. So we get x is equal to 0 or x is equal to a. So that means the curve must intersect x-axis at 2 points, at x is equal to 0 and at x is equal to a. Now to check the intersection with the y-axis, we need to substitute x is equal to 0 in the equation. So if we substitute x is equal to 0, obviously the first term becomes 0 because there is x outside the bracket, so whole term is 0, and here we have a 0 minus a outside. Inside the second bracket we get 0 minus y square, that is minus y square, is equal to 0. So simplifying, we get a y square is equal to 0, which gives us only one value, y is equal to 0. It means the curve intersects y-axis at the origin only. Now second, we have to check symmetry of the curve, whether it is symmetrical about x-axis or y-axis or about the origin or about the line y is equal to x. So as we observe, replacing x by minus x, the equation will change because there is linear power of x outside the bracket. It will make this term negative. So that means the curve is not symmetrical about y-axis. But if we replace y by minus y, the equation will remain the same because it has only even powers of y. So if we replace y by minus y, it will not change. That means the curve is symmetrical about x-axis. Since replacing y by minus y, the curve remains the same. Therefore, it must be symmetrical about x-axis. Now the next characteristic of the curve we need to discuss is asymptote. So as we observe the equation, if we open it up, we get x cube plus xy square minus ax square plus ay square is equal to 0. As we observe, the highest degree term in x is x cube and whose coefficient is constant. So that means there is no asymptote parallel to x-axis. But if we observe the highest degree term in y, which is the terms having y square, so if we take y square common out of these two terms, we get x cube plus x plus a y square, taking y square common out of these two terms, minus ax square as it is equal to 0. So highest degree term in y is y square, whose coefficient is x plus 1, which is a variable coefficient. So obviously there is an asymptote parallel to y-axis, which may be obtained by equating this variable coefficient to 0, that is x plus a is equal to 0 or x is equal to minus a. So this is an asymptote parallel to y-axis. Now the next characteristic of the curve which we are going to discuss is double point. For that purpose, we need to first open all these brackets. So we get x cube plus xy square minus ax square plus ay square is equal to 0. And then we have to assume the whole left hand side as f xy. So fxy is equal to x cube plus xy square minus ax square plus ay square. Now we have to differentiate it with respect to x partially. So we get del f over del x is equal to 3x square plus y square minus 2ax. Now differentiating the function partially with respect to y, we get del f over del y. Differential of first term is 0 and we get 2xy. Derivative of this term is also 0 partially with respect to y, and derivative of this term is 2ay. So now for double points, del f over del x is equal to del f over del y, both are equal to 0. So it implies that 3x square plus y square minus 2ax is equal to 0, make it 1, and 2xy plus 2ay is equal to 0, make it 2. From 2, if we take 2y common out of it, we get x plus a is equal to 0. And here we have two possibilities, either y is equal to 0 or x plus a is equal to 0 or x is equal to minus a. Now if y is equal to 0, putting in equation number 1, we get 3x square minus 2ax is equal to 0, or taking x common out of these two terms, we get 3x minus 2a inside the bracket, and here we get x is equal to 0 or x is equal to 2a upon 3. From here, if we substitute x is equal to minus a in equation number 1, we get 3a square plus y square and minus 2a y. So because x is negative a, so it becomes minus minus plus 2a square is equal to 0. So y square plus 5a square is equal to 0, which is not possible because sum of two positive terms may not be negative, and being square, y square and a square must be positive. So this is impossible. So we have only two double points. One is 0, 0 and other is 2a upon 3, 0. Now we have to check the nature of these double points taking second order derivative of these two. So if we differentiate del f over del x with respect to x again, we get del 2f over del x square is equal to first term 6x, second term is y square, so partial derivative of y square is 0, and partial derivative of minus 2ax is minus 2a. If we differentiate del f over del y with respect to x partially again, so we get del 2f over del y del x del y is equal to, so partially with respect to x, if we differentiate first term we get 2y, and second term is 0, and finally differentiate del f over del y with respect to y again, we get del 2f over del y square, and which is equal to 2x plus 2a. Now we need to check the values of del 2f over del x square and del 2f over del x del y, del 2f over del y square at these double points to check their natures. So first we have to check 0, 0, so we have to first substitute x is equal to 0, y is equal to 0 in del 2f over del x square, and that is equal to 6 into 0, 0 minus 2a, that is minus 2a. So minus 2a is the value of the second order derivative, partial derivative of f with respect to x, del 2f over del x square at 0, 0, that is minus 2a. Now similarly del 2f over del x del y at 0, 0. This is 2y, so putting x is equal to 0, y is equal to 0, that means we get 0. And finally del 2f over del y square at 0, 0, we get 2 into x0 plus 2a, that is 2a. So now we need to find out the value of expression del 2f over del x del y 0, 0 whole square minus del 2f over del x square at 0, 0 into del 2f over del y square at 0, 0. That is equal to the value of del 2f over del x del y at 0, 0 is 0, so it is 0, 0 square is 0 minus del 2f over del x square, which is minus 2a into del f over del 2f over del y square at 0, 0, which is 2a. So we write 2a. Simplifying, we get 0, minus into minus plus, so 0 plus 2 to the 4 a square. Finally we get 4a square, and which is greater than 0 for all values of a, because a square may not be negative. So we came to the conclusion that 0, 0 is a node. Thus 0, 0 is a node. Now if we take the summary of our analysis, this is the short summary. Intersection with the x-axis, as we have calculated, at x-axis the curve intersects at 2 points 1 or 0, 0 and 1 a comma 0. So at x-axis 0 comma 0 and a comma 0, but at y-axis only 0 comma 0 is the point of intersection. Now let us trace the curve. So let us start with the point of intersection at x-axis 0 comma 0 and a comma 0. So 0 comma 0, that is origin, and a comma 0, that is the point at a distance of a unit from the origin at x-axis. Assuming that a is a positive, on x-axis, these are the 2 points of intersection. On y-axis, only origin is the point of intersection. That is clear. So the curve must intersect x-axis at 2 points and y at the origin only 1 point. So say this kind of branch we have. Second is the symmetry. It is symmetrical about x-axis, so the curve is the same below the x-axis as it is above x-axis. So by symmetry we may trace the same part of the curve below the x-axis. So this much part is clear. And now asymptote is x is equal to minus a. That means a straight line parallel to y-axis at the distance of a unit from the origin. So this is the line x is equal to minus a parallel to y-axis. X is equal to minus a. This is the asymptote. So obviously, if it is asymptote, the branch of the curve seems to be parallel to it. That means intersecting at infinity. So we make a branch of the curve very close to this line, apparently parallel to it. And because it is symmetrical, so the same branch will be below the x-axis. So this is, and obviously 0 0 is the node, so evidently this is the node at 0 0, because the curve intersect itself at 0 0 such that there may be two tangents at the point of intersection, so this is a node. So this is how we trace a curve.